talks, I would like to invite our faculty members to kindly come forward for the felicitation of a distinguished speaker. First, I request Rashmi ma'am and Archana ma'am to kindly felicitate Dr. Reshma Rastogi, Associate Professor, Department of Computer Science and Engineering, South Asian University, Delhi.
क्लास वाले का है
क्लास वाले को मैंने डाल दिया भैया सर ने
बैठो बैठो
Next, I request Mohan sir and Harvinder sir to kindly felicitate Dr. Ompal sir, Associate Professor, Department of Computer Science, University of Delhi.
टू है
Now let me take a moment to introduce our eminent
सुबह डाला था
speakers
ना
for today's session.
वो सुबह के लिए अभी टू का है
Dr. Reshma Rastogi, an associate professor at South Asian University, is an eminent researcher in machine learning with over 65 journal papers, 40 conference papers. She did her PhD degree in machine learning from the Indian Institute of Technology, Delhi in 2008. She served in industry for 6 years before joining South Asian University in 2013. Her pioneering work on twin support vector machines has been cited over 1900 times and has been a subject of review articles in multiple highly reputed journals. She has co-authored 2 books, including Twin Support Vector Machines Modules, Extensions and Applications, and Financial Mathematics and Introduction. She has supervised 5 PhD students and more than 40 master students. Her current research interests include quantum machine learning, image processing, financial modeling, and optimization. Now let me introduce you to our next distinguished speaker. Dr. Om Pal is an associate professor in the Department of Computer Science, University of Delhi. With over 20 years of academics and research experience, he holds degrees in computer science and engineering, management, MS in cryptography from IIT Bombay, cyber law and a PhD in information security from Jamia Millia Islamia. He has previously served as a scientist at the Ministry of Electronics and Information Technology, Government of India, where he contributed to national projects on cryptography, information security, the Digital Personal Data Protection Bill 2022. A prolific researcher, Dr. Paul has published extensively in reputed international journals and conferences and has authored 2 books, Unleashing the Potentials of Blockchain Technology for Healthcare Industries and Intelligent Cybersecurity for Modern Networks. Dr. Paul serves as convener in the Bureau of Indian Standards, has supervised several PhD and master students, delivered over 50 invited talks, and continues to shape India's digital and cybersecurity landscape. We are truly privileged to learn from such accomplished experts today. On behalf of the organizers, I warmly welcome all participants and look forward to fruitful discussion and insights. Now, without any further delay, I would like to invite our first speaker of this session, Dr. Reshma Rastogi, to deliver her talk on quantum mechanics machine learning.
दो पकड़ना
पढ़ ले
Thank you for the introduction and thank you for the organizer for inviting me for this workshop. So without any further delay, I start with the topic on quantum machine learning. But before I start with quantum machine learning, I would first like to know that from the audience, how many of you actually know what is machine learning? Anybody from the audience who knows machine learning? What is machine learning? Okay, let me start with a simple example for that. So when you prepare for your exams, right, you try to do as many questions as you want. Why do you do as many questions? In the hope that when you will see your question paper, one of them will be there, so that it will save your time, right? On the similar lines, if I connect your brain with machine, right? So your brain is kind of a machine which actually tries to see the examples before the exam. So it's kind of a training yourself before the exam, so that when you see the question paper, which question paper has maybe one or two questions from what you have done so far and few more new questions. So basically you are testing your mind on the unseen questions. The same replica is being done in machine learning. So when you see your brain is a machine. The data set, the questions which you have learned so far is your training samples, right? And based on the training samples, based on the practice which you have done, you perform in your exam. That is what the testing, how you do the testing in machine learning. So this is a replica of what we actually do in machine learning. We try to build up some algorithms. This is different from AI. In AI is totally based on rule based. So if you have seen a tree structure, you are at a level that you go left or right, or for that matter you follow Google Map also. It's a rule based, as in when you have to go from one source to a destination, then you have to follow the path. So that is a rule based system. But in the case of machine learning, we actually try to get hold from the data itself. So the more the data is given to the machine, better it will perform. Similarly, more questions when you will solve, better you will perform in the exam. So it's totally a replica of that, right? So with that as a benchmark, and if we start with this slide, which says that machine learning is nothing but the amalgamation of several fields, right? In your bachelor's, you do study mathematics, you do study statistics, then some of you are on neurosciences. So basically, machine learning takes the information from computer science. If you talk about the complexity of the algorithm, so unless you have done a complexity analysis, you will not be able to do a complexity analysis for an algorithm which you are going to build up, right? So you're taking something from computer science, something from statistics, probability, and everything. Optimization do also play a crucial role in machine learning algorithms. So while they build a machine learning algorithms, the idea is that any real life problem which you have, you want to frame that in form of an optimization problem, and you try to see how you can solve it. For example, a transportation problem, traffic salesman problem. For example, if you want to deliver pizza from the pizza to different sites, the order which has been placed. So what will be the shortest route? So in designing such a problem, it will be a kind of an optimization problem which you need to solve, right? Now, if it is giving you a closed form solution, then we are ready to go with that. But if it is not, then we try to find out a solution using some heuristic algorithms. So, learning pattern from the data in order to draw inferences. That's what machine learning is. So, if I talk about machine learning, it's a designing of an algorithm which takes the data and learn the model from it. So, for example, all of us use emails, right? And most of the emails you tag that as a spam. And once you have tagged it as a spam, it generally moves to a spam folder. Then how do you tag a spam? How do the algorithm behind that actually sees that this is a spam? Because the choice of keywords from one user to another user changes, right? So when you design a keyword, it also, right? So then designing or picking up those keywords and the model which is at the back end that tries to find the keywords and based on the keywords it decides whether the email is a spam or not spam. Although it looks very simple, but
Keywords.
imagine if you have, for example, okay, let me put it this way. If I ask you to find out a keyword from a book, the best way to do is you go to the index and find out whether that keyword is being based on which pages, right? On a similar lines, when an algorithm at the back end tries to find out whether this keyword is a keyword belonging to a spam or not, it tries to see those keywords in particular emails and that particular email is being sent to the spam folder. So this is how the classification is being done. So here the classification is playing a role where I am distributing a mail based on the keywords to a spam or to a non-spam folder. Then we have the regression problem. Regression here would be to find out the pattern in a given data. Right? Everybody now, tries to see the stock markets or try to see how the USD is performing in terms of INR. So it follows a particular pattern, and if you try to follow that pattern and based on that if you want to do some kind of analysis, that is basically what is regression. So when we talk about machine learning broadly talks about these. So it's an umbrella, and under that umbrella you have classification, regression, and clustering models. So basically it is data type. So the type of a data will decide whether it's a classification problem, regression problem, or a clustering problem. So let me give you taxonomy for machine learning. So when we talk about machine learning, we have broader framework of supervised learning, where the feature is been assigned to you. What that means? See, when you do some examples or some questions, then the teacher comes and checks and tells you that this is whether done correctly or not, then that is when supervised by a teacher. On a similar lines, when you have a data which is being labeled, for example, if I ask you that this is an apple and this is an orange, right? I have tagged it with an apple and an orange, or a boy and a girl. So I have tagged it with a boy and a girl. Because based on those characteristics, going forward, I am going to find a classifier, right? So here we are learning with the help of label data. Now the tag is always given to us, but now with this big data coming in, not every data is tagged. That's the big problem nowadays. So now if it is a huge data, and if we try to tag each and every data, then it's going to create a mess. So nowadays we just have a handful of samples which are tagged and the remaining samples are untagged, right? And that is why we manage to semi-supervised learning. So some examples for supervised learning, as I already told you, is classification, regression, or ranking. So when you type a keyword on a Google, right, you get a pages there out, right? And then that comes with some importance, with some ranking. How that ranking is being defined. At the back end, there's a Google page algorithm which actually gives you this kind of ranking based on your previous choices or based on your previous preferences which you have done. So then the other learning is unsupervised learning, where there is no label, right? So you are doing clustering over there. So when the features are not given to you, it's basically when the labels are not given to you and based on features, if you are doing classification, it's basically clustering. And there we do dimension reduction and other unsupervised probability density estimation algorithms are there. Then this third type of learning is what is called reinforcement learning. It is where based, like I hope you have played chess with AI, right? So what does this do? When you play chess with AI, you do an action, and based on that action, AI comes back and do another action, right? So, and at the end, what is the reward? Reward is the one who wins the game. So within every action, there is a reward associated with it, right? So in case of reinforcement learning, we learn with the help of environment. There is no past data available with us, right? It's based totally on the environment in which we are working with, right? So, and there are other types of learning, like for example, semi-supervised learning, active learning. There are other several types of learning in machine learning field. similarly, if I have image data set of dog versus cat, right? So this is again a binary classification problem where we have two classes, cat and dog. Now based on, so now see, machine learning doesn't understand an image. What it wants from you is to get the features out of it. So we have to do some kind of feature extraction, and based on the feature extraction, we build up an algorithm. And then once the ML algorithm is set out there, then a new data which comes to us, we then try to classify this test image with the help of the algorithm which we have made to whether it's a cat or a dog. So this is a life cycle, right? You do feature extraction, you have the data in the form of vectors or matrices, you build a machine learning algorithm, and when a new test sample comes in, you try to classify based on this classifier into dog versus cat, right? So now here when we say feature extraction, machine learning needs this feature extraction, whereas if you do deep learning, nowadays people are talking about deep learning. Why? Because they don't want to actually do feature extraction also. Because when you do feature extraction, there are several computer vision techniques which are being involved when you deal with the images, right? So in that scenario, if you want to do if you want to avoid feature extraction, you go to deep learning models. Alright, so this was the for the supervised learning flow. And if I go with the unsupervised learning workflow, there's only a simple difference that we don't have tag associated with the sample. So if I have to blindly say that the people sitting out here, if I want to classify who is from Delhi, who is not from Delhi, then I am not using a tag here. Who is residing in Delhi, who is not residing in Delhi, or who is residing in NCR region, right? So here if I am not using that tag and based on the information, apart from this information that the person is living in Delhi or in NCR, we are classifying them into two categories, that is what is called cluster, right? So here again we do, so here these images are being given to me, but they are not tagged this time. They are not said that whether they are the image for a dog or a cat. So we do feature extraction, we make a machine learning algorithm, and the only step which is not being done over here is that the tags are not being used. So we have done feature extraction, based on feature extraction we have been clustering. Some well-known algorithms in this line of work are K-means algorithm, which generally people know, and this is the easiest one, but there are certain development being already done in this domain also. Then, as I said, for reinforcement learning, this is an optimal policy algorithm where you have to design, you have to synthesis based the environment. So based on the environment current state, I observe and then I take a step, a state, right? And then based on the state, I will give it a reward, and based on that circle, I'm going to perform my task. So this is what reinforcement learning is. This is pretty different from that of unsupervised and supervised. This is a data set of human brain. Now here the idea is that based on this, if you see there are certain red and blue points distribution over here. So this is a brain of a healthy person. Down is a image of a healthy person, and this is for the Alzheimer. So based on this distribution only, we can categorize a person having Alzheimer versus a normal patient, right? So this topography of this brain is giving us a data based on which we are trying to classify it into a normal or a Alzheimer patient. That's another story that in Alzheimer also there are certain stages, right? So now this is what we have already discussed. So the point is that in any machine learning algorithm, which is a data-driven algorithm, you don't need any rules, you don't build any rules, you just apply any model. So this is, let's say for example, based on the distribution of the data, I am going to find out a classifier. Now how I'm going to find a classifier, that's another story. For example, it can be mean-based classifier, right? So I can find out, let's say, make girls in one and boys in another, and try to find out center quotient, and then say that if with this respect of a girl, if the 7 others are also girls, then this information is kind of spreading out, and then we get hold of this information propagation, and with that we are going to do the classification. So as I was saying, span filtering is you've been given a data, and based on the features, the keywords, we are going to define whether it's a spam name or a non-spam name. So, and the character recognition, which is basically a multi-class. So if you have to characterize from 0 to 10, which is the digit recognition problem, again it's a multi-class problem. So binary is where we have only 2 classes, and multi-class is where we have more than 2 classes, right? So character recognition also, we have 26 characters. So how to classify them is what is called as multi-classification problem. Now then there are certain structured input. So, and then we have image data sets also. So this is, I'm trying to tell you what kind of data sets do occur in machine learning and what can we get with machine learning environments. Now the point comes here when we have to decide whether the algorithm which we have considered is kind of doing overfitting or not. Right? By overfitting it means that let's say this is the 2 classes, and if I am getting this curve, this black curve, then I am able to classify the blue samples with that of red samples, provided I try to ignore these samples, blue samples, which are on the sides of red region, right? So, but if I try to classify them also, then I am trying to get some kind of non-linear surface or an irregular surface. So if I try to do this, then I am overfitting with the data. Right? So in the machine learning algorithm, there are 2 aspects. One is the error, which we try to monitor, and the other is the overfitting part, which we also try to control. So based on the model in hand, we would try to have a linear classifier or a non-linear classifier. And if it is a non-linear classifier, it is somehow doing overfitting, and we want to avoid that overfitting. So this is what a machine learning in mathematical sense would mean, that would be given unknown function, and you would try to find out a model, and this is my parameter. So how I am going to choose a model? How I am going to find this optimal parameter is what machine learning answers. So this is how we import the data. We have the data set, we do some kind of encoding, we try to find out this function, and then we try to measure how this function has performed. Right? And how we are going to do this? We are going to find out this error. Let's say y minus pi. I will give you a simple example. Let's say in this class also, we would like to have boys versus girls. And one of the characteristics which we have taken is the length of the hair. But let's say there is some boy who has already have a long hair. But does that mean that that boy is a girl? Right? So that kind of error is being computed when we try to see how good our classifier is, how good the classifier has learned the rule, the data set properties. Right? So now let's talk about quantum machine learning. So my whole objective was to tell you that in machine learning we are trying to find out a model, and that model is trying to minimize an error. Right? So when we talk about quantum, now I will take a pause over here before I introduce this quantum. See, in the era of 1960s, neural network was already in place, right? But the theory of neural network was there, but no one was using neural network. The reason behind that, only a perceptron model can be worked out. The reason behind that was that we don't have that infrastructure support to execute those algorithms. Computers were not in place at that time. So then there was some hesitance to use neural networks. So it came to a halt. And then in 1990s, machine learning came into play, 2008, deep learning again came back, and the whole theory which was being developed with the neural network was being moved on for the deep learning networks also. But what was the reason? The reason was since 1960 there was no infrastructure support, but now in 2008 we do have fast computers to do all the calculations. So it is not just the theory which is important, it is the implementation part which makes that theory important to us. That's what my idea of quantum here is. Do we have quantum machine learning? Right? Since we have machine learning, it's easy to see what can be extended to quantum domain. But then again, the problem here is, do we have quantum computers? Because the challenge which was there in 1960 is the same challenge which we have today. There, we didn't have computers, and so the theory of neural network faded off. But we are not that bad now, right? We do have some quantum computers, but the limitations is there. We just have, so here we talk about qubits. There in the computers, we talk about bits, right? We have 0, 1 bits. Based on binary bits, we do the calculations. In this case, we have qubits. So then in qubits, here we have, till now we just have 1000 qubit machine available. So we have a kind of a restriction to do this computation of quantum machine learning. But otherwise, the theory is well in place. So now if I talk about quantum, then there is this whole sort of domain of quantum computing where this entanglement, superposition and interference are the three key features based on which we are actually looking to exponentially large Hilbert space. See, but the idea here is that, for example, when we talk about Simpson problems, random sequence problem, it's an NP-hard problem. What do we mean by NP-hard problem? A problem which does not solve in a polynomial time. Right? So, how do we solve that? We try to give a solution and then we check whether that solution satisfies all the constraints or not. This is what we mean by NP-hard problem. On the similar lines, in quantum also, the idea is that we do have a large search space. And why do we have a search space? Because of these properties of entanglement, superposition and interferences. Right? So when we say quantum machine learning, it's basically the amalgamation of quantum computing with machine learning. So whatever machine learning techniques we have learned so far will adapt the concept of quantum computing, and that leads to the quantum. For example, if I have deep learning, I can talk about the quantum learning. If I have kernel methods, I can have quantum kernels also, and so on. Right? So when we say quantum machine learning, again we are talking about four classes of algorithms. One is CC, which means you have classical data and classical algorithm to solve. Then we have QC, which means you have quantum data, but then the classical machine learning algorithms are being used to solve it. When we are talking about CQ, we are dealing with classical data, but the algorithm is quantum, which means that you are taking classical data to a quantum space, and then in quantum space we are using quantum algorithm to solve. Then we have QQ, which means you have quantum data and quantum algorithm to solve the problem. Right? So this is a paper which talks about power of data in quantum machine learning. If you are interested, you should learn this. This paper basically motivates you to use quantum machine learning only when it is required. Right? Because when we have a classical data and that classical problem can be solved using simple classical machine learning algorithm, then why to use qubit? Why to use quantum computers? Right? When we do have simple computers to solve that particular problem. Right? So this basically tells you all those scenarios where you should use quantum machine learning. So as I was saying that there was no the quantum computer, so there are certain, like for example Google, Penguin, and so there are certain these devices are basically cloud-based devices. So these are cloud-based processors which gives you the option to learn for a small span of time, right? So if you see, as I was telling about that we have these four domains. So we have a classical data and the quantum algorithm to work. So when we say quantum algorithm, they need quantum data. So we need to process the data in the quantum space first, and then quantum algorithm will be used to solve the problem. Right? So now when we have quantum data, we need quantum algorithm, and that quantum algorithms are available on these cloud-based servers. So the idea is very simple. We have, on the left side, we have classical machine learning algorithm. On the right side, we have quantum machine learning algorithm. So the classical, you have a data. Data is processed in forward direction, and based on its performance, the weights are being learned. This is basically a classical neural network. On the right hand side, this data, which was earlier classical data, converted to a quantum qubits, and then we create a circle. So here it's just a linear combination of weights, whereas in this case you have circles. And then again you have to see the performance of each and every circuit to find out whether the choice of the circuit which is being made here is usable or not. So let me give you an idea how do we do that in classical sense. So we have a data set, we split the data into training and testing, and we use the training data to build the feature and do the learn. So there are three steps involved here. One is to first divide the data into two parts, training and testing, finding out the linear model, right, based on the feature extraction, and then a cost function is associated which we call as a loss function to figure it out how the performance of the model is. So on a similar line, if I say project into quantum space, first I have to send the data to a quantum space. So that means I have to create a qubit, right? So we will start with the data. Feature induction is a optional point over here. So we use some quantum embedding techniques. As I said, classical data cannot be sent to quantum algorithm. You have to first convert classical data to a quantum data, and then quantum data will be sent to quantum algorithms. So we first use some quantum embedding techniques, and then we create this kind of a circuit, right? And this circuit will take into consideration all the properties which I told you earlier, the entanglement, inference. So here, and then whatever we learn from this, we set, because the data initially was classical. So we get this back information in a classical sense only, right? So which means that an image, which in a classical data was an image, will be a qubit in a quantum space, right? So now the point comes in that how do we learn these parameters, right? How do we learn these parameters? There we learn the parameters based on the loss function. So obviously the same projection has to be done in the quantum space. So here also, based on a loss function, we are going to find out whether the current set of circuit developed is meaningful or not, right? So this is the basic step. So here I have tried to create a quantum replication of simple classical machine learning. We have a data, we try to encode this data, right? Then here we make a model, here also we make a model, but here we make a model based on
data model output.
Here we do measurements, here also we do finding in inference of the given circuit which we have selected. So both the algorithm works parallelly. Here everything is in a classical sense, the data is classical, the model is classical machine learning, but here everything is
Function here.
So now the point comes, how do we import this data, right? Because unless you take your data to a quantum space, you cannot work with it. So these are some encoding techniques. So the idea is that you either you go with the basis encoding, right? Then you go with the amplitude encoding, or you go with an angle encoding, or you can take all the three encodings together also, right? So there you are converting, for example, in basis encoding, let's say if you have a data 1, 3, right? Then in quantum space, this representation of 1 will be 0, 1 because I'm using 2 qubits only. way, basis encoding is not suggested because, as I said, we just have 1000 qubit machines available to us. So then we have amplitude encoding. Amplitude encoding basically talks about some kind of a normalization. So if I have 4 features, I do normalization, and everything is written down with the help of qubits. So if you see here, we have 0, 0, 0, 1, 1, 0 and 1, 1. These are the 4 qubits available with us. Then we have angle encoding scheme. So angle encoding again looks into the proper. So it's basically a wave channel. So here we talk about projecting my classical data into the quantum using angular encoding, right? So if I talk about these 3 methods, then this I have talked in terms of which is best and which is not, depending upon the infrastructure which is available, what are the qubits available for us with us to do the computation, right? So for example, if you have this kind of data, right, which is having 3 classes, it's non-linear data, this when we use the or when projected in a quantum space using angular encoding, then you see the data becomes linearized. So the qubit comes to a linear. So this is another example. Now, when we say entanglement or a feature map, I'm not sure whether you are aware of kernel functions in classical machine learning. On a similar lines, this concept is built up, and we talk about a feature map in quantum space. So these are the 5 options have been used for a data set. So I will show you the results on this, and this basically just to show that the performance of classical is seen as that of a quantum. So that doesn't motivate us to use quantum. Why? Because when we say quantum, in quantum means to be used only for a problem which cannot be solved using classical methods. Right? So this is the algorithm. What we do is that we have the properties of superposition and inferences. We start with all 0 qubits. We make a circuit, we run, and then get hold of the final solution to a particular problem depending upon how bad or good we have performed in this kind of arbitrary circuits. So now the question is that let's say we have come up with this theory of developing the circuits, then how can we build up such a computer? And if such a computer is being built, then what can it do? Right? So I was referring to NP-hard problem. The NP-hard problem where you give a solution and then test if the solution is applicable for a particular problem or not. On the similar lines, here also we have what we call as the NRs. Then this is basically being used to find out whether the given circuit definition is doable for my particular problem or not. Right? And so we have different set of circuits designs, and then we see which circuit is going to do good for us. Right. There are certain variants for it. I'm not getting into that. So once we have generated circuit and the final circuit has been selected, we count the probability, and that is how we transform the quantum interference back to classical ones. So we talk in terms of probabilities, the final outcome in the classical node. So this was basically an algorithm used for classification. I thought I will be discussing the quantum part of this algorithm. So just 4-5 slides more, just bear with me with that. So we have this two-class problem labeled
लाइव
I try to find a classifier which takes
लगाओ के इधर
gives me which divides
नेट ले लिया
the
मैंने
content of it by encoding the data into the quantum Hilbert space. Is 72 of designing a quantum computer with so many qubits, right? So then we have to make a trade-off. Where to go? Whether
चार्ज पे खाना है
to ask me
कहाँ
and
लगाओगे हेमंत
suggest
हेमंत
go on
हेमंत
quantum
ये बस
science
चार्ज निकाल दो
whenever
मेरे बैग में
there is a
चार्जर रखा
requirement
निकाल
of a
दो
problem, right? Where there is a requirement of using those properties of coherence,
हाँ
entanglement,
क्यों
and
अंदर ले लो
sequence. Otherwise, it's better to stay in a for example, if you see, I have made a comparison to get a large search space and solve NP hard problems which you cannot solve using classical machine. At what cost? So if you can answer that, then you can use quantum and going
जाओ
forward,
बैठो
you will definitely use quantum, right? Because the kind of data face, the kind of concept you're going to have, you have to, there's no option to use
आशीष
quantum. But then, again, you should know a line where to use quantum
चार्ज
and
नहीं है
where you can do with
चार्ज हुआ तो होगा
classical machine learning also. Right? So that's all. This is you have a bachelor's program and
कितना है
master's program. We do have a master's in computer science, bachelor based on your any curriculum. We have 1 year master's program. We have 2 years master's program. We have MCA and okay. Thank you so much.
थैंक यू मैम
Thank you so much, ma'am, for such an insightful and enriching session. Now, without any further ado, I would like to invite our next distinguished speaker, Dr. Omkar Sir. Sir will enlighten us on the topic Introduction to Quantum Computing.
कौन सी एक घंटा और क्या हो गया भाई बैठ जाओ हाँ हाँ बहुत बढ़िया बहुत बढ़िया अरे 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 गेट बंद करो
To propose the vote of thanks for this session, may I now invite our teacher in charge of
करेगा कौन सी चार्ज में लगा सुपर चार्ज में
We extend our sincere thanks to Dr. Reshma for her valuable insights on quantum machine learning. We have got some good pointers to start with in this area now. When your talk was very thought-provoking, thank you so much for your time today. Thank you so much.
कहाँ से तार वाला पीछे बुला रहे हो किसी कौन थे आप भाई क्या हुआ भैया यहाँ जस्टिस जगह वाले हमारे वो
We will discuss what is quantum computing. Why we are moving from classical computing to quantum computing. So, if we talk about the speed up, or if you can complete a task quickly, let's say कोई ऐसा task है आपको बहुत जल्दी complete करना है, तो उसके लिए आपको क्या और उसको आपको क्या है सिमुलेट करना है। सिमुलेट करने के बाद आपको फिर ये बताना है कि एक्चुअल में नेक्स्ट प्रिडिक्ट करना चाहते हैं 2 दिन के बाद उसका कोई मतलब नहीं है, क्योंकि उसमें भी मोर देन वन मेथड से मिलेगा, लेकिन आपके जो अप्रोच है मोर देन वन नेक्स्ट देयर आर 3 पॉइंट्स, पॉइंट ए, पॉइंट बी, पॉइंट about the water transport and air transport. You have only one choice, that is road transport. So it means first you will move from A to C, then C to D. Okay. Suppose आपके पास पहले सिर्फ 2 व्हीलर का इन्वेंशन है, आपको काफी टाइम लग रहा है 2 व्हीलर से 4 व्हीलर बनाने, अभी हो गया जहाँ आपका 2 व्हीलर मैक्स आपको 60, 70, 80 तक जा सकता है, अब 4 व्हीलर से और भी आगे जा पा रहे हैं। फिर आपने क्या किया, ट्रेन पर आ गए, बुलेट ट्रेन पर आ गए, ठीक है। इसके सबके बाद भी आप देख रहे हैं कि अभी भी